Hey guys, and welcome back. My name is Miss Danielson, and today we're doing an introductory lesson to solving linear equations. Up until now, we've mostly just focused on algebraic expressions, but I hope you join us for our lessons on setting up simple expressions, because in that lesson, we talked about function machines. And in this lesson, we're going to see function machines again as we rearrange these equations and undo the functions in the function machine. I'll link that setting up simple expressions lesson down for you below, along with a lesson on function machines themselves, in case you're interested on learning a bit more about those skills before we start this lesson. When we're asked to solve an equation, first of all, we need to be told what some expression is equal to. That's the difference between an expression and an equation. Expressions cannot be solved because we don't know what they're equal to. When we solve an equation, what we're actually asked to do is find the value of the variable in the equation. So when you have a set of calculations being performed on a variable, you need to know what the result of that would be so that you can work backwards to find the value of that variable. We do this by getting the variable on its own, by undoing the operations that are being performed on it. So in this example here, I can clearly see that the expression 5 plus x is equal to 12. But what is x on its own? To get the variable on its own, we need to undo whatever's been done to it, but keep the equation balanced. So whatever's done to one side of the equation must also be done to the other side of the equation. So in this example here, x has been added to 5 to make 12. So to undo this addition, we'll subtract 5 from both sides of the equation. That's going to get our x on its own, because 5 plus x minus 5 leaves us with just the x, and x must be equal to 12 minus 5. 12 minus 5 is 7, so x must be equal to 7. That's the solution to our equation. Now let's write down the steps we follow to solve an equation. First, we want to solve our equations vertically, that is from top to bottom. So we line our equal signs up. That way you can clearly see what's happened to the left-hand side of our equation has also happened to the right-hand side of our equation. Next, we're going to solve the equation to get the variable on its own. Look at what's been done to the variable so that we can undo that. To undo an addition, we need to subtract. To undo a subtraction, we need to add. To undo a multiplication, we need to divide. And to undo a division, we need to multiply. Make sure that your equation is balanced. Again, following step 1, we'll see that when we undo any of these operations to one side of the equation, we're also undoing these operations on the opposite side of the equation. We saw that in the example that we just did before, where when we took the 5 away from the left-hand side of the equation, we also took the 5 away from the right-hand side of the equation. Step 5 is more a rule than it is a step, but it's very important. The order of terms must be maintained. If a term has been moved, that is added or subtracted from one side of the equation to the other side of the equation, it needs to come after the term that's already there. So for example, when I move the 5 to the right-hand side of the equation, it's new to that side of the equation. It has just arrived on the right-hand side, so the 12 must stay first, then the 5 comes after. Step 6, again, is really just a reminder that in algebra, the multiplication signs are often left out. So if you see something like 4a, you need to know that that means 4 times a. And a on its own is the same thing as 1a or 1 times a. Now, keeping those steps and reminders in mind, let's work through another example. This example involves addition, and remember that the opposite of adding is subtracting. But before we even start, remember step 1, we are working vertically. That is, we're working from top to bottom. And to keep everything lined up, we'll line up our equal sign. So before we do anything, equal sign under the equal sign. Now, if I want to get the v on its own, we need to get rid of that plus 3, and the opposite of plus 3 is minus 3. We're subtracting 3 from both sides of the equations to keep it balanced, You may not need to write that minus 3 that I've written in yellow there. I'm really just writing that for your benefit so that you can understand where the next step of your working comes from. So the next line of working is simply v is equal to 17 minus 3. Now that the v is on its own, v is equal to 14. And that's the solution to our equation. To add to our steps, however, is we should always check our answer by substituting it back into the original equation. Now you may want to do that mentally in future, but definitely for your note for this example, you should write this down so you can understand how you're expected to check your answer in future. If v equals 14 and v plus 3 equals 17, does 14 plus 3 equal 17? Yes, it does. So our check has worked out. V is definitely equal to 14. Let's try another one. This time we've got 12a equals 48. And remember, when you've got a number directly in front of a variable, they're being multiplied. So we need to undo this multiplication. But before we even start, remember step 1, we are working vertically. Let's line up our equal signs. Next, to get that a on its own, we need to undo a multiplication by 12, and the opposite of multiply is divide, so we'll divide both sides by 12 to keep things balanced. That will get the a on its own on the left-hand side, and on the right-hand side, we'll have 48 divided by 12. Again, you may not need to write the divide by 12s that I wrote in yellow there. I just write them to make sure you're clear on why a is equal to 48 divided by 12. Next, a must be equal to this answer. A must be equal to 4. So that's our solution to this equation. But of course, we always check our answers by substituting them back into the original equation. So if a is equal to 4, does that mean that 12 4s are 48? 12 times 4 is 48, so yes, it does. A must be equal to 4. We've just checked it. And this time we want to get b on its own. Be careful because this time b has got 5 subtracted from it. Now we need to be careful when we're looking at subtractions because the order of terms in a subtraction is more important than in an addition or a multiplication. For example, 5 minus 2, which we should all mentally be able to work out, is 3. That's not the same thing as 2 minus 5. When you take a big number away from a smaller number, your answer ends up being negative. So that would be negative 3. So looking at this equation here, b minus 5 is equal to 8. The 5 is being subtracted from b. So to get the b on its own, we need to unsubtract the 5. That is the opposite of subtracting 5. First, let's line up our equal signs, and then let's add 5 to both sides. That will get the b on its own because, of course, b minus 5 plus 5 will cancel out to be just b. And b is equal to 8 plus 5, which is 13. So our solution to this equation is b equals 13. But of course, we always check. Whether you write it down or not, you should always at least go through this mental check. If b is equal to 13, does that mean that 13 minus 5 equals 8? Well, 13 minus 5 does equal 8, so yes, it's true. b must be equal to 13. We do have the correct solution. One last example before we go on to something a little bit harder, but this is already a little bit different. Here we've got a fraction, but just remember that fractions are divisions. You're going to want to copy this example down for sure. Also note that you need to take care of because in divisions, much like in subtractions, the order of terms is more important than in multiplications or additions. For example, 8 divided by 2, we should all be able to mentally work that out. That's 4. That's not the same thing as 2 divided by 8. 2 over 8, you would be able to see that that fraction simplifies, is a quarter. Either way, you should definitely know that when you divide a smaller number by a bigger number, there is no way that your answer is going to be a whole number. It will be a fraction or decimal answer. So x is being divided by 7. So if we want to get rid of the 7, we need to do the opposite of divide, which is multiply. But remember, before we even do that, line up those equal signs. And then we're going to multiply both sides by 7. X divided by 7, then multiplied by 7 will leave x just as itself. So x is equal to 5 times 7, which is 35. So our solution to this equation is x equals 35. Let's do our check. If x is equal to 35, does that mean that 35 divided by 7 is equal to 5? 35 divided by 7 is 5. So, yes, it does. So we've got the correct solution. X is equal to 35. Let's move on now to something slightly more challenging, two-step equations. That's where there's more than one operation to be performed in an equation, and we need to make sure that they're done or undone in the correct order. In order to do this, you're going to need to remember your Bedmass order of operations. If you haven't seen that lesson, I'm linking it down below. And we're going to use function machines to explain this a bit more clearly for you. So I'll link down our lesson on setting up simple expressions, as well as our function machine lessons down below too for you. But in our setting up simple expressions lesson, we saw a function machine that did just this. It asked us to multiply whatever the input value was by 4, and then subtract 7 from that answer. So in this example, where you've got an equation, 4w minus 7 equals 5, you need to think about what's happening to the variable. The variable is being multiplied by 4. And then that answer has 7 subtracted from it. And then the output value, the result from this calculation, is 5. So if we want to work out what w was, we want to work these calculations through backwards. But very first thing, let's line up our equal signs. Let's think of what's happening to w, and let's undo those operations, but in reverse order. So looking at my function machine, from the output value back to w, we need to undo the subtract 7 first. And the opposite of subtracting 7 is adding 7. So add 7 to both sides, and hopefully you can see that 4w minus 7 plus 7 will leave us with just 4w on the left-hand side. So 4w is equal to 5 plus 7 on the right-hand side. Let's simplify that a bit. So 4w must be equal to, I've lined up my equal signs here so you can see where everything's coming from. The 5 plus 7 adds together, working vertically, we put its answer below, 12. 4w must be equal to 12. Next, we want to get that w completely on its own, so we need to get rid of the 4. The 4, which is directly in front of our variable, is multiplying by our variable. And as you can see from our function machine, we've already gotten rid of the minus 7. Let's get rid of that 4. The opposite of multiplying by 4 is dividing by 4. So we divide both sides by 4, and hopefully you can see that 4 times w divided by 4 will leave us with just w. So w equals 12 over 4. Remember, fractions need division, so 12 divided by 4. Now we just need to simplify this to find our solution. W is equal to the answer of 12 divided by 4, which we write underneath, that's 3. W equals 3 is our solution to this equation. Since that was a two-step equation, it took us a bit longer and there were more opportunities there to make mistakes. We should definitely check our answer. I highly recommend that you write your checks down. So here we go. If W is equal to 3, that means that 4W minus 7 must equal 5, or 4 3's minus 7. Does that equal 5? 4 3's, that means 4 times 3. That's 12. Is 12 minus 7 5? Yes, it is. So we've got the correct answer. W must be equal to 3. Let's try another one, this time with brackets. Again, remember your Bedmass order of operations. The B in Bedmass stands for brackets, and that means that we always work out the calculation that's inside the brackets first. Once again, let me show you a function machine which explains the order in which we perform these operations. First, we need to do the calculation inside the brackets, which is adding 5 to our variable, and then that answer gets multiplied by 3. So our two-step function machine, add 5, multiply by 3, gives us an output of 9. So we want to go backwards through this machine, undoing these operations to get the t on its own again. First, let's line up our equal signs. Then let's undo that multiply by 3. The opposite of multiplying by 3 is divide by 3. So hopefully you can see that 3 times the answer of t plus 5, then divided by 3, we'll just cancel those 3's out. So we have t plus 5 is equal to 9 over 3. Remember that fraction means divide. So let's simplify that. 9 divided by 3 is 3. Now we still have a 5 that's over here bothering our t. We want our t on its own. We've gone through our function machine backwards. We've gotten rid of that multiply by 3 by dividing by 3. Let's get rid of that plus 5 by subtracting 5 from both sides. Hopefully you can see that t plus 5 minus 5 would just be t. So that means t is equal to 3 minus 5. Simplifying that, t must therefore be equal to the answer of 3 minus 5, which we write underneath, it's minus 2. T equals minus 2. Again, we've come to our solution where we've got our variable on its own, and it's equal to some number value. Let's check that that number value is correct. So if t is equal to negative 2, let's put that into our original equation. First, let's work out what's inside the brackets. Minus 2 plus 5 is positive 3. So that's 3 times 3. Is that equal to 9? Yes, it is. So our answer is correct. T must be equal to negative 2. Now I hope you're finding these function machines here helpful for you to figure out what operation happens first and how do I undo these operations in the reverse order. But if you don't like the function machines, they're not necessary. You don't need to draw them. They're just there for those of you who do find them helpful. Time to go on to some practice now. This first row are just single operation equations, so they should be fairly straightforward. If you need a function machine, you can use one, but you shouldn't need one. The one question that might trip you up is question 2 here, because I've got the p on the right-hand side. But that's not a problem. You just want to get the p on its own, so send that 3 over to the left-hand side. For our next row, we've got some divisions and multiplications here. But again, it should be fairly straightforward. It's only single operation equations, so function machines should not be necessary, but again, you can use them if you like. For the next row, we've got 2 operation equations now, and some of them have brackets. So if you need function machines, feel free to do that. So time for you to hit pause, copy these questions. Don't just guess at your answers, please. They're relatively easy and straightforward questions to begin with, so it's more about the method than it is about getting the answer right. So go ahead and hit pause, work it through, and hit play when you're ready to take up not just your answers, but also your working. I hope you've had a chance to hit pause, because here come your answers. For question 1, to get v on its own, we'll minus the 8. For question 2, to get p on its own, we'll minus the 3. For question 3, to get b on its own, we'll minus the 15. For question 4, to get n on its own, we will add the 15. For question 5, to get v on its own, we multiply by 8. For question 6, to get b on its own, we divide by 14. And take care when we divide a negative number by a positive number, our answer is negative. If you need a lesson on integer calculation, have a look at the description box below. For question 7, to get the b on its own, we will multiply by negative 2. Notice we changed the division to a multiplication. We did not change the sign of the minus 2. And of course, remember negative multiplied by negative gives a positive answer. For question 8, to get the n on its own, we'll divide by 10. For question 9, two-step question now, first we'll subtract the 11, then we'll divide by the 3. For question 10, this is a bit of a trick question here. Negative 4 is added to 2m. Adding a negative is the same thing as subtracting. So this is basically the same thing as 2m minus 4. The opposite of subtracting 4 is adding 4. So 2m equals 8 plus 4. And divide by 2. Question 11, here we've got brackets. Remember, when there's brackets, usually we work out what's inside the bracket first. So we would first add 8 to the m, and then multiply that answer by 2. But when we work backwards to undo these operations, we'll first get rid of the 2. So divide by 2, then subtract the 8. Again, first we would work out what's inside the bracket, so subtract the 7, and then multiply that answer by 3. Working backwards to undo this, however, first we'll divide by the 3, then we'll add the 7. There are other methods for dealing with brackets as well, however. We could always expand the brackets out before we solved. So for question 11, expanding that bracket out means multiplying the 2 not just by the 8, but by the 8 and then also by the m. So 2 times 8, 16, and 2 times m, 2m. That's equal to 18. So if you first expanded out the brackets, we can then rearrange and solve this equation that remains and not worry about the brackets changing our order of operations. So to get the m on its own, it's being multiplied by 2 and 16's added. So let's go backwards. Let's subtract the 16. Then let's divide by the 2. Let's do the same alternate method for question 12 now. First, let's expand that bracket out. 3 times y is 3y, and 3 times negative 7 is negative 21. So 3y minus 21 equals 15. To get the y on its own, think what's happening to the y. It's being multiplied by 3, and then 21 is taken away from it. Let's go backwards. Let's first get rid of that minus 21. Opposite of minus 21, add it. And then the opposite of multiply by 3, divide by 3. As you can see, question 11 and 12 have the same answers regardless of the method that you use to solve them. Now, how did you do? I'd be very interested to hear who prefers the first method I showed for question 11 and 12, and who prefers to expand the brackets out before working it through. If you had any problems or doubts, please let me know down in the comments section. Otherwise, really great job with a good introduction to solving equations, guys. We're going to be doing a lot of algebraic equations in the future, so it's important that you have a good, strong base. So keep practicing, and I'll see you soon.